This is an introduction to the use of the terminology and notation of differentials. I like to introduce this as early as possible in my calculus class. So here's the situation. For example, of the many things you could use differentials for, we've got a rod. It's essentially a one-dimensional object, just a thin rod, and we're measuring the temperature along it. That's T is the temperature as a function of x, the position along the rod. And we discover it has a graph something like this. So the rod's hotter over here on the right, it's cooler on the left, and the temperature is particularly sensitive to position. It changes fastest with respect to position right around x equals 2. What we know numerically is that we measure right at 2. We have a very precise measurement right at x equals 2, and we discover it's 100 degrees Celsius. But we don't have a formula for this necessarily. I want to get away from the idea that everything might have to have a formula. But we do have, we've been able to figure out that that f prime of x, the derivative, f prime of 2 rather, the derivative of that temperature function at 2 is equal to 200 degrees Celsius per centimeter. And I want to know more about what that means, how to think about it, and how to use it. And that's where differentials are really useful. So we have this alternate notation for the derivative of a function. It's often referred to as Leibniz notation because he invented it, as d big T dx, d of the output variable, the dependent variable, by d of the independent variable. And I want to point out that this really has a very concrete meaning and can be very nicely used. So here's what we want to think about, what dx and dt mean. Some people will tell you that these don't have independent meanings at all, but they really can be used as completely reasonable quantities. So when we're looking at derivatives, we're looking at rates of change, and we would like to start from this point 2, and we'd like to understand what happens when we go a little bit away from 2, either to the left or right, but I'll stay right for right now, and predict what's the change in the output variable. So, for example, if I go over a little dx, I'm going to exaggerate how much dx, or how much the change in x might be a bit. Ideally, here's what we'd like to be able to do. We'd like to go over an amount delta x. So that's our very standard terminology for the change in x. And we'd like to predict how much the temperature, the output function, actually changes. Now that's going to be called delta t. So when we use deltas, those are actual changes in the variables. And it's especially important distinction for the output variable, the dependent variable. So if for any delta x I use, changing from this base point value 2, if I can predict how much the temperature changes, I'm done. I've very accurately predicted exactly what that temperature is going to be. But unfortunately, that's the hard part. That's something we can't do just from the derivative information. Because what's the derivative? Remember what the derivative is. It is the slope of the tangent line here. And as soon as we go away from this point, that function is going to tend to curve away from its tangent line somewhat. And so we're not going to be able to use that tangent line approximation to get an exact value for delta t. But what we can do is we can at least get an approximate version of delta t. And that is what dt is going to be. So dt, by definition, is this whole change. It is the change in the function that we would get if it were a straight line, if it were its own tangent line. And this is how differential calculus works. We look at a function, we take that first derivative, and we use that to assume, to pretend that the function was a straight line all along. Or another way to say it is we're approximating what the function really does, and things like the actual change in the function, delta t, by the theoretical change, the approximate idealized linear change, dt. Now, there's a bit of an asymmetry here. Since we have control of the function of the variable x, that's the independent variable, there needs to be no distinction between delta x, which is what we would call it if we're kind of aiming for the actual change in t, and dx, which is the notation we're going to use if we don't quite go for delta t and we're aiming for dt. So delta x and dx, the inputs, these are just two different names for the same thing. On the other hand, delta t, when we're looking at the output variable, that is not equal to dt. Delta t is the change we'd really like to get, but depends on all the complexity of this curvy function. Dt is the idealized change that we're going to predict as an approximation. Okay, so how does that relate to the derivative? Okay, remember f prime of x, that's the slope of the tangent line. The slope of the tangent line is the rise over the run of the tangent line, and the rise is by definition called dt, and the run is dx. That's exactly what this says. The slope of the tangent line is, for any choice of run value that we put in, that's going to be dx, it's the corresponding rise of the tangent line divided by the run that we chose. Okay, so we're going to use that to predict roughly what the actual change in the temperature will be, and we're going to remember to advertise as long as this gets pretty big. Whenever this gets pretty big, it's going to be a poor approximation, but when this is small, we're hoping that it's a situation like here where the curve is not very different from the tangent line, and it'll be a pretty decent approximation. All right, so for example, we've got this 200 number, okay, and I want to show you how we would use that. Okay, so we've got a situation where dt dx is known to be 200, and it's degrees Celsius per centimeter, but I'll express the units right now. Okay, so one thing we could do is, for example, if we put in a dx, a known change horizontally, we can predict what the dt is. For example, if dx equals 0.5 centimeters, that might be pushing it a bit on going somewhat far based on this picture, but at least approximately, dt is going to be 200 times dx. Rise equals slope times run. That's another way to talk about slope. And that's going to be 200 times 0.5, or 100 degrees Celsius. So what does that say? It doesn't say that we're absolutely sure that precisely the temperature has gone up by 100 degrees Celsius when we go over a half centimeter. Instead, we're saying that the straight line prediction, the approximation, is 100 degrees Celsius change. But that's all we can do here. It's the only number we can really provide, and it's definitely better than nothing. A little bit more intricate use of that. Let's see if I can just get a little more room. I don't want to erase the picture, I don't think. So what if we knew, like we have a safety margin, we want to know how far we can go right and still have the temperature be like under 120. So let's figure out how far we could go right and have the temperature actually be at 120. Okay, we'd like to find this point on the purple curve that actually matches 120 and see how far we can go right. We'd like to start with delta t for a smaller triangle. Let's erase this. Okay, delta t for a smaller triangle and get delta x. That's not going to happen. But we could say, well, what if dt, that's going to go, maybe I'll use a red here, that's going to go to the red line. Notice it's not that different because this isn't very big. We're going to say, what if dt is 20? What's dx going to be? What's my allowable change in input to accommodate some reasonable change in output? Okay, so now I'm going to substitute in dt is 20. So 20 over dx, not 3 lines, equals 200. So we still have that if we're pretending this function is just a straight line, that rise over run is known to be 200. And now it's just that we know the rise and we know the slope and we want to get the mystery run. But it's not hard. Just multiply by dx and divide by 200. 20 over 200, or 0.1, equals dx. So this says the straight line approximate prediction is that we can walk 0.1 centimeter to the right, and roughly we should only have that 20-degree change in temperature. In the second part, I'll just do a couple more examples where it's about position and velocity.